Hi, today we're going to talk about a summary of curve sketching. So let's talk about what our goal is. What we want to be able to do is graph an entire function without using a graphing utility or randomly picking x values, plugging them in, getting ordered pairs, and hope we see the shape of the graph forming. So let's recall some information we've been talking about so far in this class. We'll start with our intercepts. Remember, intercepts are where the graph crosses the x and y axis. So we have our x-intercepts, which happen when y equals 0, and we have our y-intercepts, which happen when x equals 0. Sometimes these will be really easy to calculate, and then they give us good ordered pairs we know we need the graph to go through, and sometimes they won't be so easy to calculate, and so we just won't use them at all. Another thing we've discussed are vertical and horizontal asymptotes. So does the function have any? And you will need the appropriate limits to justify whether or not. So I'll remind you what those are. If the limit as x either shoots off to positive infinity or shoots down to negative infinity of f of x approaches a single finite value L, then y equals L is a horizontal asymptote. So as x is getting bigger and bigger and bigger in the positive direction, your function starts to level off and look almost horizontal. Or as x gets really, really, really big in the negative direction, and again, it seems to level off and be almost horizontal. That's your horizontal asymptote. Your vertical asymptote, if either your right-hand limit or your left-hand limit as x approaches a of f of x gives you one of the infinities, then you have a vertical asymptote. So as x gets really, really, really close to a from the right, and your function either shoots up to positive infinity or shoots down to negative infinity, you're going to have a vertical asymptote. Or as x gets really, really, really close to a from the left, your function shoots up to positive infinity or shoots down to negative infinity, then you will have a vertical asymptote. And one of the things that we said is that really good candidates to check these limits are any x values that make the denominator equal to 0. Now, just because the value makes the denominator 0 does not guarantee it gives you a vertical asymptote, but it's a good place to start. Other things we've talked about is where your function is increasing and decreasing. Remember, wherever your derivative is positive, then your function is increasing, and wherever your derivative is negative, your function is decreasing. And then a function can only change from increasing to decreasing or decreasing to increasing, either where the function itself is not defined or where the derivative is not defined or the derivative is 0, which we call those critical values. Does your function have any local extrema? Remember, local extrema can only be located at critical points. So if you recall the first derivative test, if your derivative switches from positive to negative at c, well, that means that your function switches from increasing to decreasing at c, and then you would have a local maximum. If your derivative switches from negative to positive, which means your original function would be switching from decreasing to increasing at c, then you would have a local minimum. And if your derivative does not change signs, then you don't have a local extrema there. Another thing we can talk about is the concavity of the function. Where is your function concave upwards? Where is it concave downwards? And if you recall, wherever the second derivative is positive, your function is concave upwards, which means the tangent lines lie below the curve. And wherever your second derivative is negative, then your function is concave downwards, which means your tangent lines lie above the curve. If you recall, a function can only change concavity where the second derivative is undefined or where the second derivative is 0, like those critical values, but just using the second derivative. And does your graph have any points of inflection? Remember, points of inflection happen wherever your function switches concavity, either goes from concave up to concave down or concave down to concave up. So let's put it all together and sketch a curve. So let's sketch x cubed over 3 minus 5x squared over 2 minus 6x plus 2. Now the x-intercepts, they're not really going to make a whole lot of sense for us to calculate because I don't want to factor that and set that factor is equal to 0, so I'm going to skip those. But the y-intercept should be fairly easy because you just plug in x equals 0, goes away, goes away, goes away, and we're left with 2. So we know that for a fact that the ordered pair 0, 2 is on the graph, and the graph is going to go through the y-axis there. Now, hopefully it's clear to you that this function is not going to have any asymptotes. So as x gets really, really big in the positive or negative direction, shooting off to positive or negative infinity, this is really just going to shoot off to positive or negative infinity. So you're not going to have a level off horizontal. And there are no x values that make the denominator equal to 0, so there's nowhere where our function could possibly shoot off to positive or negative infinity at one given a value. Let's talk about where it's increasing, decreasing, and the relative extrema. So remember, to find where it's increasing and decreasing, we need to determine where the derivative is positive and negative. And the derivative can only change signs at these critical values, which is where the derivative is 0 or where the derivative is undefined. So I'm going to recall the function itself, but I wrote it different this time. Remember, it was x cubed over 3. Well, dividing by 3 is the same thing as multiplying by the reciprocal 1/3. So instead of x cubed over 3, I'm going to write this as 1/3 x cubed. Same thing here. Instead of 5x squared over 2, I'm going to write it as 5/2 x squared. So now when I go to take the derivative, bring the 3 down, 1/3 times 3 is 1. Bring the 2 down, the 2's will cancel, and I have 5x minus 6. So my derivative is x squared minus 5x minus 6. Now, critical values happen wherever the derivative is 0 or undefined. This is a polynomial, this is a quadratic, it's never going to be undefined. So these critical values are going to happen where that's equal to 0. So I'll set the derivative equal to 0, factor, set the factors equal to 0, and I see I have two critical values, one at 6 and one at -1. All right, so I'll draw my number line labeling those critical values. And now my next step is to find the intervals that are outside and in between those. So now what I know is that my derivative is either completely positive or completely negative on this entire interval, because these are the only places they can switch. So it's either all positive or all negative here, same thing here, and same thing here. So I'm going to pick these test x values, one from each of these intervals, and I'm going to plug them into the derivative. And so I can say when I plug in -2, I can determine if my derivative is positive or negative. Whatever holds true for -2 will hold true for all values in this interval. So if I plug in -2 squared minus 5 times -2 minus 6 gives me 8. Plug in this next test x value, 0. 0 squared minus 5 times 0 minus 6 gives me -6. And plug in this test value, 7. Now, one of the things that we've mentioned is that you can plug it into the unfactored form of the derivative or the factored form. And for larger values, it's typically easier to plug it into the factored form. So I'll do 7 minus 6 times 7 plus 1, and that gives me 8. So as you can see, for this test x, I got a positive, so that means on this entire interval, the derivative is positive. For this test x, I got a negative, so on this entire interval, I'm negative. And for this test x, the derivative was positive, so on this entire interval, the derivative will be positive. So take a look at that. That's enough information for us to be able to determine entirely where this function is increasing, decreasing, and any local extrema. So as we can see, the derivative was positive on the first and last interval. So this function is increasing from -infinity to -1 and from 6 to infinity. It was decreasing from -1 to 6. Now, did my derivative switch from positive to negative anywhere? It did right here, so this is going to give me a local maximum. Did my derivative switch from negative to positive anywhere? It did, so at 6 we're going to have a local minimum. So our local maximum is at the ordered pair -1, f evaluated at -1, which I will need to calculate. And my local minimum is at 6, my function evaluated at 6, which again I will need to calculate. So back into the original function, I'm going to plug in -1. -1 cubed over 3 minus 5 times -1 squared over 2 minus 6 times -1 plus 2 gives me 31/6. Now I'll plug in 6, and I get -52. So my local maximum is actually at the ordered pair -1, 31/6, and my local minimum is at the ordered pair 6, -52. Now let's discuss the concavity of this graph. So for concavity, we need to use the second derivative. So we'll take the derivative again, and we get 2x minus 5. 2x minus 5 is linear. That's never going to be undefined. So we set it equal to 0, and we get 5/2 is the one value where the function can change from concave up to concave down. That's the only place that the second derivative can change from positive to negative or negative to positive. So I already have my number line here, so now I'll add these intervals that are outside between that little value there. And again, I'll pick test values, one from each of these. Doesn't matter what the value is, as long as you pick one x value from each of the intervals and you plug them in. Now up here, we're going to plug them into the second derivative, because if the second derivative is positive, we're concave up. And if the second derivative is negative, we are concave down. When I plug in 0, 2 times 0 minus 5 gives me -5. When I plug in 3, 2 times 3 is 6, minus 5 is 1. So when I plugged in this test value on this interval, I got a negative. That means that the entire second derivative is negative on that whole interval. Here I got a positive, so the second derivative is positive on this entire interval. So now we can see that this function is concave upwards from 5/2 to infinity. It's concave downwards from negative infinity to 5/2. And it does have a point of inflection because it did switch concavity at 5/2, and we will need to figure out the y value by plugging 5/2 into the original function to get negative 281 over 12. So the point of inflection is at 5/2, negative 281 over 12. And so now with all this information, I am ready to graph my function. So as you can see here, I have a little XY axis. It's not the greatest. I'm trying to draw on my computer. I'm doing the best I can. But the information that we have, we do know that at y equals 2, right about here at 0, 2, we have our y-intercept. We know my function is increasing from negative infinity to negative 1, so I'm going to label negative 1. And I know that my function is decreasing from negative 1 to 6, so I'm going to go ahead and label 6. I have a local minimum at 6, negative 52, so I'm going to label way down here 6, negative 52. I know I have a local maximum at negative 1, 31, 6, which is a little over 5. So right about here is going to be my negative 1, 31, 6. I'm concave up till negative infinity to about 3/2, so I'll label that right about there. And I'm concave down from negative infinity, 5/2. My bad, 5/2, there we go. And concave down from negative infinity up to 5/2. I do have a point of inflection at 5/2, negative 281 over 12, which is about negative 23, so we'll put that right about there as my point of inflection. So I know I'm increasing up to negative 1, being concave up, so I need to make sure I'm nice and having my tangent lines above the graph. And then I'm going to come back down, going through this y-intercept here, all the way down to this point of inflection, where I'm now going to change directions to become concave up, so that my tangent lines lie above or below my graph. And then I'm going to have this local minimum right here. So I'm going to be concave upwards to connect that and come right back up, something like that. So that's about what my function is going to look like. Now again, this is a sketch. It's not perfect, and it doesn't need to be perfect. So now let's take a look at what this actual graph does in fact look like. And so I graphed it using Desmos, and as you can see, it is increasing up to negative 1, 31, 6. Then it comes back down, still being concave up, goes through this y-intercept 0, 2, right to here at my point of inflection, where you can see the tangent lines go from being above the graph to now being below the graph. I'm concave down all the way down through this local minimum at 6, negative 52, and all the way see the tangent lines are still below the curve. So our graph lines up with what the actual graph looks like. It's not the greatest, but I don't care about perfection. I care that you can see what the graph is doing, and using the information that you know about it increasing, decreasing, local extrema, concavity, and points of inflection, that you have a rough sketch of what the function's doing. In my next video, I'll do another example.